Okay, so in the last video, we looked at static electricity in lightning and stuff like that. This time we're going to look at current electricity, which is the electricity we actually use. So current electricity, so the symbol for current is I. So we've got the current there. Symbol is I. It's for historical reasons and also to avoid confusion with another um, quantity of electricity. So a battery, cell, or generator is the supply of electric potential energy. A battery, for example, has a positive cathode and a negative anode, and there is a difference in electric potential between those points. So remember that potential energy is that there is some energy stored with the potential to do work, if we remember back to our energy section. When the cathode and anode are connected by a conductor, so when they are connected by a conductor, electrons flow from the negative anode to the positive cathode. So a conductor is something that allows the flow of electrons. So copper, we often use copper, that's a very good conductor. And most metals will conduct electrons. So the movement or flow of charged particles is current, and it is measured in amps or amperes. That's named for a scientist who worked on electricity. So the point here of flow charged particles is it can be any charged particle, so it can be also protons and any other form of ion as well. And we're just reiterating that the symbol for current is I. So if you don't know who this guy is, your homework is to watch The Matrix. This is Morpheus. So what if I told you I remember that a cathode is positive because I like cats? So it's actually the way I do remember which end is a cathode and anode. So if this is a battery, then this will be the cathode, and this will be the anode. So if you see this symbol, this is the battery symbol, and the long end is the positive, and the short end is the negative. And we'll look at them a few times in this. So units of current. So the SI unit of current is the ampere, like I said before. 1 ampere is equal to 1 coulomb of charge flowing past a point in 1 second. So 1 ampere equals 1 coulomb per second. And remember that 1 coulomb is equal to 6.242, I think, times 10 to the 18 electrons, or elementary charges. So 6 billion charges, essentially. So that's how many little charges are going through a single point in 1 second if you have a flow of 1 amp. So the rate of flow, so we can calculate the rate of flow of charge using this equation here. So the current is equal to Q, the charge, over time. And it just says there, current Q, and this is in your formula sheets. Now, the conventional positive direction of current is the flow of positive ions. Okay, so the positive direction is the flow of positive ions, and unfortunately, this is the opposite direction to the flow of electrons. So electrons are negatively charged, and when they were setting up their conventions for which way they wanted to choose as positive, they went around the other way and they chose it in the direction of positive ions, and unfortunately, electrons are deemed negative charges. So we will see a little example about that later. So just a few comments here on the continuity in an electrical circuit. So an electrical circuit needs to be continuous, no breaks. So that means you need to have like the wire all connected, can't have a break in it. The circuit must form a complete loop so that the charge can flow from the battery to the load. So a load will be a resistor, and then be returned to the battery. Now the current leaving the battery is the same size as the current returning to the battery. So if we have a look here, we have our battery here, our volts. We have a load, so this is resistance, and I'll just draw the other symbol for resistance as well. So it might look like that as well. So that's a resistor, and then the current goes back to the voltage. So here we have our current, and it's the same here and here, and that will depend on how big this resistance is. And we'll look at that. We'll look at the mathematical equation, which is Ohm's law. a bit later. So next I just have a selection of electricity symbols. You don't have to remember them off by heart really. We will be looking more at voltmeters and ammeters a bit later. A cell, this is like and this is a battery. So officially a battery has 2 cells, but if you draw this as a battery, that's okay as well. So if you noticed before, I just drew it like that. If you draw it as a cell, that's fine. An open switch just looks like a gate kind of thing, and then a closed switch is the closed gate. So open switch and closed gate switch. I'm not sure if I have to talk much more about that. This is just more for your reference. And then there's a bunch of other examples there as well, which we don't really cover in this course. So we've got some examples now of current. So if we determine the charge that has flowed through a torch battery, producing a current of 300 milliamps for 20 minutes. So the equation that you have in your formula sheet is the current is equal to the charge divided by time. So I'll do that one. I'll do an equal sign there. So that means that, just rearranging it, the charge is equal to the current times time. And then we're going to have the current, which is 300 milliamps, which is equal to 300 times 10 to the negative 3. Remember your prefixes, milli, and then time is going to be 20 minutes times by 60 to get it into seconds. And therefore, Q is going to be equal to 360 coulombs. So just putting that into your calculator. Coulombs. How many electrons have flowed through the torch? So remembering our equation in our static electricity, we had the number of electrons is equal to our charge divided by the charge of 1 electron. And that's going to be equal to 360 over 1.6, which equals to 2.25, so that's quite a few, times 10 to the 21 electrons. Okay, so that's actually equivalent to 2,250 billion electrons has passed through that torch in 20 minutes. It's quite a lot. Using the symbols above, draw a circuit of a torch, assuming it is a battery, a resistor, and a lamp. Indicate the conventional flow of the current and the flow of electrons, or as well as the flow of electrons. And we'll just try and wait for Word to respond. Okay, thank you, Word. Okay, then. So let's draw our battery or our cell in there. Going to have, assume it's a resistor, so I'll draw my resistors like this. And then we've got a lamp like that. Then we connect it all up. Okay, so we have our current, and it's going from positive around to negative. So I is like that. And then I'll draw it down here, but remembering that our electrons go from negative to positive. So our electrons are going to go this way, around like that. And the flow of electrons stays the same. So electrons going around that way. We could have had our I going back the other way as well. So I, and it's the same going both ways. Okay, now some problems on current, so I'll leave the video there and we'll talk about the next one later.